Roaming is the term used to describe a Wi-Fi client being handed off between wireless LAN access points, analogous to this function in a cellular network. The IEEE 802.11 standard includes the concept of a client roaming between access points, but does not specify how or under what conditions this may occur. With implementation left up to developers, widely varying, anomalous, and even unpredictable results are always a possibility. And attempting to evaluate and understand roaming behavior in free space, given all of the potential variables, can be next to impossible. That's why the octoBox from Octoscope is a vital tool for all wireless engineers. The octoBox provisions an isolated, programmable, and repeatable environment that enables design and development engineers to explore and optimize roaming behavior quickly and efficiently. To test roaming, we first place one or more access points under test in an octoBox. Using multiple octoBoxes, there is no limit to the number of APs that can be configured. We then place a client device into an octoBox as well, and connect the configuration via Octoscope's Quad-10 programmable attenuators. The Quad-10s are the key to evaluating roaming, as they can simulate motion and other signal fading under program control in an entirely predictable and repeatable manner. Randy Oltman is Octoscope's Vice President of Marketing.
The roaming automation software programs RF attenuators to ramp in opposite directions, which emulates motion of the client. The speed and direction of the emulated motion is programmable. For example, when Quad-10-1 attenuation value is increasing and Quad-10-2 attenuation value is decreasing, the emulated motion of the client is in the direction from access point 1 to access point 2. Initially, Quad-10-1 is set to a minimum value and Quad-10-2 to a maximum value to encourage the client to associate with access point 1. As Quad-10-1 is increased and Quad-10-2 is simultaneously decreased, the path loss between the client and access point 1 increases, and the data rate of the client to access point 1 link will transition to a lower rate. At the same time, path loss between the client and access point 2 decreases, as the link to access point 1 is lost due to increasing client to access point 1 path loss. The client finds access point 2 and associates with it. If the client roaming algorithm is well implemented, the client will associate with access point 2 prior to losing the link with access point 1. After the roaming script completes, the software displays a plot of ping traffic versus attenuation and time. This slide shows an example of a roaming testbed implemented using the smaller model of the octoBox. Each device in the roaming testbed can couple into the test network either over the air or via cabling. In this example configuration, we have access points cabled and a phone coupled over the air. Each device in the testbed is placed into its own octoBox for complete isolation. Conditions for roaming are created using dynamically adjusted Quad-10 programmable RF attenuators. This causes the phone to roam between access point 1 and access point 2. The roaming software simultaneously controls emulated movement of the phone while sending ping traffic from the PC to the phone. During the handover event, the ping traffic may be interrupted, which provides a visual indication of roaming speed and behavior. Additionally, a variety of interference types can be added through Octoscope's iGen signal generator for further realism.
The Octoscope roaming testbed emulates motion in a controlled, repeatable way, isolated from outside interference. The controlled environment and emulated motion provides a qualitative view of the client traffic as the device moves from one access point to another. The well-controlled, repeatable testbed makes it a lot easier to dive into the details of the roaming algorithm. This first tab gives us control over emulated motion. In our testbed, we have two electrically controlled attenuators, which are Octoscope Quad-10s. Through these attenuators, we establish a 4x4 MIMO link between the client and two access points. By varying the attenuation, we can emulate motion of the client between access point 1 and access point 2. Each time I click the green roam button, attenuators are ramping in an opposite way. After performing a roaming shift, the tool automatically provides a Results tab. On the Results tab, I can see the ramping of the attenuators here. Attenuator 1 is reducing from 60 dB to 0 dB, while simultaneously attenuator 2 is increasing from 0 dB to 60 dB. Before we started the roaming test, the client was associated with one of the two access points, and we were pinging the client with a response time of less than 10 milliseconds. Then during the roam, the actual handover, we had a gap in ping traffic. Once the client was able to associate with the other access point, you see the traffic resume. But here we are seeing a gap where the pinging stopped. There's no connectivity to the client, and in this case the handover took a very long time, approximately 3 seconds. The ramp time during that test was 1 second, but we can make the emulated movement slower, for example 5 seconds, by changing the ramp time setting. Once again, I can cause the roaming event by clicking the green button. You can see in the status bar the progress of the test, and you can also watch the time progress on this dial here. With these results now, you can see the much slower ramp time of the attenuators in the test bed. This is a 5 seconds of ramp over 60 dB of attenuation change. As a result, you can see that the client is struggling during the handover period where the ping response times get longer. We still have the same dropout of roughly 3 seconds during the handover event. You can see that we started pinging the client roughly 2 seconds prior to the start of the roaming event. This value is settable on the Roaming Operation tab here. You can also set the total duration of the ping period to the anticipated duration of the roaming event here. In this case, we set it to 10 seconds so that the pinging can overlap the entire roaming event.
Octoscope's complete array of tools enables engineers to explore roaming behavior under any conditions and to whatever depth is required. It's easy to examine a wide variety of scenarios with an unlimited number of access points. And absolute control over the RF environment assures repeatability and apples-to-apples comparisons. Note also that the test procedures we've discussed here can be applied to many other roaming scenarios, including LTE and vehicular roaming such as 802.11p. Octoscope. There is no more productive, reliable, and cost-effective way to test roaming.